Humans have always loved numbers. Unambiguous notation for numerals is attested all the way back in ancient Mesopotamia, and numeric systems in general have existed even longer. But nobody loves numbers, and in specifically big numbers, more than Googologists. Googology is an informal field of mathematics where people try to invent the biggest numbers possible, and I think the results of this deeply human competition are frankly fascinating, so I put together an iceberg chart with some findings from the Googology community. In case you don't know, anything at the top of this iceberg represents very well-known things about a topic, and things get more obscure as you go deeper. I decided to modify this a little bit, but the idea is still the same. In my iceberg, the top represents a combination of factors. Either the numbers aren't very big, they're super well known, or they're not that weird. As you go deeper, the numbers get more obscure, bigger, or generally weirder, but not necessarily all three. So, without further ado, let's get into the Googology iceberg. 1. The first number you learn, and a generally useful value, is the first natural number, meaning a number corresponding to a real-world quantity of things, and it's often used to represent a certain probability, being the same as 100%. Oh, and also, without the numbers 1 and 0, we wouldn't have developed digital computers, so we should really thank these numbers for what they do. These are the first numbers that people really consider big. They're the ones you probably said when you were a child arguing with your friends about who can say the biggest number. Whether 100, 1,000, a million, a billion, or whatever, most people consider them to be very large numbers. Let's define a function called increment. When we give it a number, it will give us the next one. This basically allows us to count. Then, let's define the plus operator. If you think about it, adding two natural numbers is just the same as repeatedly counting upwards from one of them, so addition is really just a higher form of incrementation. Then, we define multiplication, which is really just repeated addition. Exponentiation, then, is just repeated multiplication. Powers, indices, and exponents are all names for the same basic concept. This is the number that gave Googology its name. A googol is defined as a 10 to the power of 100, which is the same as a 1 with 100 zeros following it. Seen visually, it looks like this. Be happy that you're getting to see the full written form of the number, because soon they'll get so big that this won't be possible anymore. Googolplex is also a very well-known Googology number. It's defined in the same fundamental way as a googol, but instead of a 10 to the power of 100, it's a 10 to the power of a googol. That is, a 1 with a googol zeros following it. If we remember back to the first big numbers, we recall a million, a billion, a trillion, a quadrillion, and so on. The 100th one of these is called a centillion, and is equal to 10 to the power of 303. It's easy to confuse a millillion for a million, because they sound so similar, but they're actually not the same, at all. A millillion is just 10 to the power of 3003, and you may sometimes hear it referred to as a millinillion, a milliatillion, or a millitillion. 52 factorial is produced by multiplying 52 by every natural number less than itself. That is, 52 times 51 times 50 times 49, and so on. What makes this number interesting is a relatable example, playing cards. There are 52 factorial possible combinations of cards in a standard deck, meaning that, every time you shuffle a deck of cards, there's a good chance that that particular deck has never been created in the history of the entire universe. How is this? Surely 52 factorial can't be that big, right? There's a famous thought experiment that shows how gargantuan this number is. Start a timer with an initial value of 0. This timer will increase by 1 every year. Group every grain of sand on Earth into a single pile. Every 1 billion years, take 1 grain of sand and move it into a different pile. After you've moved all of the sand into the second pile, place 1 sheet of paper on the ground. Repeat the process by moving all grains of sand back into the original pile, stacking another sheet of paper on the ground every time you finish. Keep stacking papers until the height of your stack reaches the surface of Pluto. Once you finish, keep doing the same thing, but removing papers this time instead of adding them. Once you're done with that, congratulations! You're 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 Tetration is another mathematical operation that's useful in creating large numbers. Recall that a to the power of b is a multiplied by itself b times. We called this exponentiation. If we go one level deeper, we find that repeated exponentiation is called tetration. Just like how tetration was repeated exponentiation, pentation is defined as repeated tetration. Actually, it doesn't end here. We can define hexation as repeated pentation, heptation as repeated hexation, octation as repeated heptation, and so on. This process can actually go as far as we would like to take it. Centimillion is the 100,000th illion number. It has a value of 10 to the power of 300,003. As we have seen, exponentiation, tetration, pentation, hexation, and so on form a sequence of operators where each one is just a repeated version of the last. In 1976, Donald Knuth saw this and devised a way to write this idea mathematically, called Knuth arrows, or up arrow notation. In up arrow notation, a arrow b means a to the power of b. A arrow arrow b is a tetrated to b. A arrow 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 b is a pentated to b, and so on. Collectively, these extended operators are known as the hyperoperators. If we have too many arrows to conveniently write this, we can shorten it by writing the number of arrows next to the arrow symbol. After Google, this is probably the most famous Googology number. To start, think of 3 arrow 3, which is equal to 27, or 3 double arrow 3, which is equal to about 7.5 trillion. At 3 triple arrow 3, we are past the point of being able to compute the number's value with current technology. Let's go one level deeper and take 3 quadruple arrow 3 and call it G1. Then we define G2 as 3, followed by G1 arrows, followed by 3. Note that the arrow followed by a G1 here means the G1th hyperoperator. Alright, G3 can then be defined as 3, followed by G2 arrows, followed by 3, and so on. Keep repeating this until you arrive at G64. This is Graham's number. Graham's number is, famously, so big that if you tried to simultaneously visualize every digit of G, it would require so much matter and energy that your head would spontaneously become a black hole. 4cal of 1 is the same thing as Graham's number, but instead of terminating at G64, it goes until G of 1 million. Steinhaus polygons are another notation devised to represent really big numbers. A number written inside a triangle is equal to that number to the power of itself. These shapes can be nested. N double triangle is n triangle inside a triangle, which is n to the power of n to the power of n to the power of n. A triple triangle is n double triangle inside another triangle, that is to say, n to the power of n to the power of n to the power of n, all to the power of itself. This can continue ad infinitum. The next Steinhaus polygon is the square. A number inside a square is equal to that number inside of that number triangles. This pattern continues when more sides are added to the polygon. A number inside a polygon is equal to that number inside of that number polygons of one fewer side. Mega is defined as 2 inside of a Steinhaus pentagon, which is the same as 256 inside a square, which is the same as 256 inside of 256 triangles. Actually, the notation originally used when Mega was published used a circle instead of a pentagon, so you may sometimes see this. Make no mistake, it's the same as a pentagon. Except for when it isn't, because to make things confusing, there's also something called Moser's number, which is equal to a 2 inside a polygon with mega number of sides. In mathematics, a tree is a structure consisting of hierarchical nodes, where each node can have direct parents and children, and each node will only ever either have one or no parents. What we're gonna do is play a game of trees. This game will go on for a given number of rounds, and each round we can use at most that round's number of nodes to build a tree. In the first round, we only have one node to use. In the second, we can use 2. On the third, 3, and so on. Note that we could use fewer nodes if we wanted, but we always have to place at least one. But there's one more thing we have to consider. Each node of the tree has a color associated with it, and we have a limited number of colors we can use. Here, we're using 3. But what's the game? Can't we just keep going and infinitely keep adding nodes to the bottom of the tree? No, because there's another rule. Each new tree we create cannot contain any of the previous trees. Here, the second tree very obviously contains the first. But actually, the definition of contains is a bit more subtle. Rather than the direct copy and paste style definition of a tree containing another tree, we define it based on common ancestors. Here, the second tree actually contains the first, because the first common ancestor of the green and red nodes on the right is the same as on the left. So, the tree of n function is defined as the number of rounds we can play in a full game of trees if we have n colors to work with. Tree of 1 equals 1, because we only have one color to work with and therefore can't really do anything after playing the first node. Tree of 2 equals 3, as we can go a couple rounds further. Tree of 3, by comparison, is incomprehensibly large. This is, by far, the biggest number I've talked about so far. Famously, if you divided equal pieces of Tree 3 among Graham's number of people, and told them each to simultaneously visualize each digit of their respective piece, well, let's say you'd end up with Graham's number of black holes in their heads. A Turing machine is a hypothetical representation of a computer system based on state transitions. Imagine you have an endless tape of cells, where each cell can hold a value of either 0 or 1. And then, imagine you have a head which can perform certain operations. This head can move left, move right, change the cell it's touching to a 0, change the cell it's touching to a 1, or terminate. This Turing machine can actually be programmed to perform tasks. How? By using a state machine. We define a table of states and how to transition between them. We start in state A and do something different depending on whether the head reads a 0 or a 1. Let's try running this simple Turing machine. Since we start in state A and read a 0, the machine changes the cell to a 1, moves left, and enters state B, reading another 0. Then it writes a 1, moves left, and enters state C, reading a 0. This continues until the Turing machine either terminates or keeps going forever. In this example, it returned to its original state, just with a slightly different configuration for the tape. The busy beaver function is the number of ones that a Turing machine with a given number of states can write before terminating. If it doesn't terminate, it doesn't count. How big are the busy beaver numbers? Turns out, they're so big that, for extremely high values of n, it's not even possible to compute them in a finite amount of time. For lower numbers, however, the first busy beaver numbers are known. At busy beaver of 6, we can't determine the exact value anymore and must be satisfied with lower bounds. The Ackermann function is hard to visualize, but is defined as follows. The function a takes two arguments, x and y. If x equals 0, then a of x comma y equals y plus 1. If y equals 0, a of x comma y equals a of x minus 1 comma 1. Otherwise, it equals this on the screen. This is hard to grasp, so let's see an example calculation while keeping these rules in the corner. We start with a of 2 comma 0 and apply the first rule, because y equals 0. Then we simplify. We apply the third rule because neither x nor y are equal to 0. Again, we simplify. We apply the second rule on the inner function, a of 1 comma 0, as y equals 0. Then we apply the first rule in the same place, and we simplify. Since x equals 0, we apply the first rule and simplify one more time. Therefore, a of 2 comma 0 equals 3, which doesn't seem very big, but that's because we didn't choose numbers that yield a big result. If we chose 4 and 2 instead of 2 and 0, for example, we get something much bigger. There are 7 fish numbers. Each one of them are quite mathematically complex, and I can't really explain them here in a simple manner, but to put it simply, fish number 1 is based on a modified Ackermann function. Fish number 2 is based on fish number 1. Fish number 3 is based on something called the S of n map. Fish number 4 is based on fish number 3. Fish numbers 5 and 6 are based on Googological maps called the M of n and M of m and n maps, respectively. Finally, fish number 7 is the largest fish number, and is based on fish number 6, as well as Rayo's number. But what on earth is Rayo's number? Well, in 2007, January 26th, Agustin Rayo and Adam Elga were having a competition to find out who can name the biggest number. After some back and forth, Rayo came up with Rayo's number and its associated function, Rayo's function. To understand Rayo's number, you need to know what first-order set theory is, and that it's basically the language used to mathematically define objects and the relationships between them. It consists of operators you probably learnt in school, like element of, negation, conjunction, and so on. It's not very efficient for writing down small numbers, but as you get bigger, it becomes highly efficient. In Rayo's words, Rayo's number is the smallest positive integer bigger than any finite positive integer named by an expression in the language of first-order set theory with Google symbols or less. In simple terms, he's saying, take a Google symbols of first-order set theory and use them to make the biggest number possible. Then, Rayo's number is the next one after that. Even up until this day, Rayo's number is considered one of the largest numbers to have ever been invented. Chained arrows are another notation devised specifically to represent extremely large numbers. Remember back to the definitions of Knuth arrows and hyperoperators. Chained arrow notation makes use of them in its own definition. But what is the definition of chained arrow notation? First, A chain arrow B, which I'll henceforth read as A chain B for clarity, is just A arrow B, or A to the power of B. Second, A chain B chain C is A hyperoperator B, where C defines the hyperoperator. Third, A chain B chain 1 chain C is just A chain B, and everything after the 1 is thrown away. Finally, A chain B chain C chain D is, well, this. Basically, the expression is fed back into C and D, but their respective values are decreased by 1 in each expression. Again, A chain B is just A to the power of B. A chain B chain C is the Cth hyperoperator of A and B. Anything in a chain sequence after 1 is ignored, and any chain of length 4 or greater will feed into itself by decrementing the last two elements until they become 1s, eliminating them. This is a bit tough, so let's try an example calculation. Like last time, the rules will be in the corner. To evaluate this expression, you first need to apply the fourth rule. Simplify. Apply the third rule. Apply the first rule. Simplify. Apply the second rule. And so, we see that even a very simple expression using chained arrows can give us extremely massive numbers. It should be noted that chained arrows are significantly more powerful than Knuth arrows, at least for generating large numbers. The CG function was created by John Conway and Richard Guy, who also devised chain arrows. The function itself is named after them. CG of n is defined as n chained into itself n times. That is to say, CG of 1 is just 1. CG of 2 is 2 chain 2. CG of 3 is 3 chain 3 chain 3, and so on. CG of 4 is the fourth entry in the sequence, with a value of 4 chain 4 chain 4 chain 4. Conway's tetratree has a value of 3 chained 4 times. That is, 3 chain 3 chain 3 chain 3. Of course, the prefix tetra means 4, and tree means 3, so the tetratree is literally the 4 threes. Zoot-zootplex is defined as googolplex to the power of googolplex minus 1, to the power of googolplex minus 2, to the power of googolplex minus 3, and this continues until all the natural numbers less than googolplex are exhausted. What makes this number interesting, or amusing I should say, is that it was invented by a 4-year-old. Personally, at 4 years old, I can't say I even knew what a googolplex was, as most of you probably didn't either. This one is a very big topic within Googology, and I absolutely won't be able to explain all, or even a big portion of it, in this short segment. But anyway, BEEF stands for Bowers Exploding Array Function. Or maybe Bowers Extended Array Function? I've seen sources that call it both, but it seems like Bowers Exploding Array Function is more commonly used. It's another notation for writing big numbers, like Knuth arrows or chained arrows, with one difference. It's horrendously more powerful than both of those. In BEEF, A array n b equals A with the nth hyperoperator of b. For example, A array 1b equals A to the power of b. A double array 1b is defined as b layers of arrays with A on each side. Basically, you expand an array of A b times over itself. If we take A double array 1, 3, we'll get a 3 deep layer of A arrays. For values other than 1, we do it a bit differently. Instead of nesting the arrays, we expand them out like this, decreasing the number inside the braces by 1 in the expansion. So A double array 2, 3 will give us this, which doesn't seem like too big of a number, but it's positively ginormous. Why? First, expand out the second brackets, and you'll get this. But then, you need to expand out the first brackets, this time using the second bracket's expansion as the number of times to expand. It should be clear that this is a very, very big number. For numbers of brackets bigger than 2, the same logic applies. If the number inside the brackets is 1, the arrays get nested. If it's greater than 1, you expand out and decrement. In BEEF notation, you can write large amounts of brackets in a similar way to writing Knuth arrows, by adding the number of brackets next to the closing bracket. Alternatively, you can use the other array notation, which looks like this and encodes the same information. By using this array notation, you can even go further and recursively apply the previous operation. BEEF also has something called the array of operator, the expression A array of B, which is be an A-length array full of B's. With the second order array of operator, you can take this even further, applying the array of operator a second time by using the first result as the new size of the array, like this. There's no reason to stop at second order array of, and we can go arbitrarily far with this notation. We can write the array of operator as the subscript of an array if we'd like, or even embed it directly into the notation for the array itself. While this is how BEEF works at a fundamental level, you should keep in mind that these are the absolute basics, and BEEF gets much more complicated as you go on. There's not even an agreed upon definition for some of the higher level stuff. Gongulus is the first number we've seen that is defined using BEEF. Since it's hard to explain how this number really comes about, I think it just suffices to say that it's bigger than Graham's number, but smaller than tree of 3. First, take a mia 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 lokapua, which is defined like this. Then, put it in an expression. Use it as the size of an array of expression of L's. Finally, put the whole thing in another array. The L here means this number is using a technique in BEEF called a legion array, which, unfortunately, I can't explain here, with the L100 meaning 100 L's in a row. The comma subscript on the array means that its value is used as the size of a recursive array of operation. Have you been asking how we even know that some of these numbers are bigger than others? I mean, at some point they're so big that it seems as if size comparison is irrelevant and perhaps not even possible. The thing is, most of these numbers are defined in terms of a function or sequence, such as Graham's number being the 64th entry in its sequence, or tree of 3 being the 3rd entry in its sequence. The fast-growing hierarchy tells us how fast these functions grow, and how large they can become within a given amount of time. This is all order of magnitude level rather than completely exact, but that's all you really need in Googology. On the Googology wiki, for example, you will see that many numbers have one of these under them. As a rule of thumb, the bigger the magnitude of this expression is for a number, the bigger the magnitude of the number. I'm dramatically oversimplifying, but the main thing to know is that fast-growing hierarchy gives Googologists a good way to compare the numbers. oh my gosh, oh my gosh, oh my gosh is defined in a notation called hyperextended cascading E notation. Since we haven't talked about this notation, I hope it's enough to say that this number is within the same ballpark as the lowest bound estimate for tree of 3. Bubawamba is defined using beef as the array 10, 10, 100, subscript 2 arrays of 10. It's bigger than some of the numbers we've already seen, including Mega, Moser's number, Graham's number, and others. Oh, also, it's used as the name for a geometry dash level, so that's pretty fun. The Xi function is based on something called SKI combinator calculus, which is a theoretical, mathematical model for representing computation using only 3 functions and nothing else. There are the I, K, and S functions. I of x is the identity function, and will just output whatever you give it. K of x, y will just give you x, discarding its second argument. S of x, y, z will form a pair with y and y of z, then apply x over it. Note that here, x, y, and z are all also functions defined using i's, k's, and x's. Traditionally, SKI calculus is written without the parentheses and commas, like this, but I think it'll help a bit with understandability if I space them out like this, so that's what I'm gonna do. Let's try an example calculation to wrap our heads around this. First, we need to apply the second rule. Then, apply the third rule. Finally, apply the second rule. Thus, we see that k of s of k, I, s, and I will simplify, that is to say reduce, to just x. Note that on every step of evaluation, we just did the simplest thing possible and evaluated the leftmost operation without worrying about anything else. In the form described here, SKI calculus is about as powerful as a simple Turing machine, but we can actually take it much further by adding another function. The omega function takes 3 arguments, x, y, and z. If x reduces to the function I, omega reduces to y. Otherwise, it reduces to z. Let's try another example calculation. We take this expression and notice that its first function is omega, so we apply the fourth rule. In order to use it, we need to see how the first argument will reduce. So apply the first rule, apply the second rule, and there we go. The first argument reduces to I. Thus, the whole expression reduces to the second argument k. This is our result. With this, the Xi function is defined as the length of the longest possible reduced string of SKI omega functions given an unreduced string of SKI omega functions of length n. Note that if the output is infinite, or if it just keeps growing to infinity as you keep reducing it, it doesn't count. The result of the Xi function is known for small values. Initially it grows quite slowly, but it soon speeds up, and eventually becomes so large that it cannot even be computed in a finite amount of time. Bigfoot is conceptually similar to Rayo's number, but instead of using Rayo's function, it uses something called the foot function. This function is a more general form of Rayo's function, which is done by generalizing first-order set theory into something called first-order oodle theory. Its definition is foot to the 10 of a googol. Here, foot to the 10 means a tenfold application of the foot function. Oblivion is also similar to Rayo's number, just greater in magnitude and scope. Oblivion, according to its creator, is the largest number defined using no more than a congulus symbols in some k of gongulus system, with a k of n system being a complete and well-defined system of mathematics that can be described with no more than n symbols. The numbers congulus and gongulus are defined like this in beef notation, and we've actually already touched on gongulus. Basically, Oblivion is a more massive version of Rayo's number. It also has a cousin. Speaking of which, to simplify the definition, utter oblivion recursively uses oblivion to create bigger and bigger mathematical systems, then uses oblivion number of symbols to generate the biggest possible finite number in the last system. Despite the fact that it, and its cousin, are considered ill-defined by many Googologists, they're still very cool numbers. In case you don't know, XKCD is a very popular webcomic focusing on humor about science, mathematics, programming, etc. In its 207th release, the comic features a panel describing a number obtained by calling the Ackermann function with Graham's number as the arguments. This became known as the XKCD number. It's the first true example we've seen of a salad number. Basically, a number created by haphazardly throwing together disparate Googologisms, rather than trying to do anything interesting with them. Transcendental integers are another Googology concept defined in terms of Turing machines. Imagine a Turing machine which has a proof of, at most, 2 to the 1000 symbols long, showing that it will halt. If it can't be proven to halt, it doesn't count. A transcendental integer is any integer greater than or equal to the number of steps required for this Turing machine to halt, given the prior proof conditions. Well, actually, it's greater than or equal to the number of steps required for any Turing machine to halt, no matter how big that is. Nucleoquarksel is defined in beef as the array 200, 200, //2. The triple slash here is another way to use Legion arrays in beef, so I won't explain it in detail. Suffice to say, it's possible that Nucleoquarksel is larger than tree of 3, at least for the lower bound. Also, Nucleoquarksel is actually the 4th entry in a series of numbers, all made by the same guy. It's Nucleoxul with a quad prefix embedded into it. Big stands for bewilderingly, incomprehensibly ginormous Googologism, and was created by the same guy who invented the Nucleoxul series of numbers. In terms of size, it's probably comparable to Nucleoquarksel, which would make it bigger than Tree 3. By the way, the reason I'm saying probably or possible here is because at this scale, the notations used for most of these numbers are simply not well defined enough to make a reliable judgment. Flannery of Ukrainian Town isn't really a number so much as the collective name of a series of 144 numbers invented by a member of the Googology community. I like to think of it as a number album, to take a metaphor from the music world. Some of my favorite entries are Hawks, which equals 13, Dynamite, which equals the 16-bit signed integer limit, TNT, which equals the 32-bit signed integer limit, Vatican City, which is 1456, Zeus, which is 1,000,000 minus 1, and Greasy Investment, which... never mind, let's just move on. Terrible Tethrothoth Carta God's Godgilus is defined in hyper-extended cascading E notation, like this. But personally, I don't think that's the most interesting part of it. The most interesting part is the name. I mean, just look at it. You take Tethrothoth, turn it terrible, which is a way of forming numbers in the hyper-extended cascading E notation, turn it terrible again, take the number God's Godgilus, and fuse them together in an unholy experiment. I mean, this is just straight up the number equivalent of a taxonomical hierarchy. The full name of this number is... Stardust Onion from the future. Oh yeah, and it's equal to about tree of G onion. Onion is about 21 quadrillion, by the way. Large number garden number is possibly the largest number ever invented in human history, perhaps even in the history of the universe. Since it's quite mathematically challenging, and frankly I don't trust myself to explain it, I'll summarize it by saying that it was created by creating a function that extends higher order set theory to make big numbers, then applying that function to itself, like this. The superscripts signify repeated operations, as we should be used to in Googology. Large number garden number is significantly larger than Graham's number, tree of 3, Nucleoquarksel, Rao's number, the busy beaver numbers, and basically everything we have talked about. And at this moment, Googologists are certainly prodding around the boundaries of the large number garden number, trying to see if it really stands up to scrutiny. But as for us, I think now is as good a place as any to end.